This is your expected value screencast. Let's get started. This equation right here is the expected value equation. So what it's saying is that the expected value, which is what you expect to earn when you're doing probability, when you're playing a game or something like that, will be equal to the payoff for your first probability times that probability plus the payoff for your second probability times that probability, and so forth for how many different situations that you are. Then this note right here is that the payoff should take into account any buy-in price. So a lot of the times when you play a game, whether it's at a casino or just at your home or whatever, you have to pay to play the game, and so you have to take that into account. So we'll see an example of that problem in a second. So our first problem says, what is the expected value or expectation? That's a different way that they'll ask you the question, is what is the expectation that Hannah wins $10 if a die rolls a 6 and she loses $1 otherwise. Let's move this up so we can write. Let's get started. So our probability of rolling 6 is the same as any other kind of roll. So it's 1/6 for a die, and the probability of rolling not 6 is going to be 5/6, because you can roll a 1, a 2, a 3, a 4, or a 5, and there's 6 total options. So our earnings, so this will be like P1, this will be like P2. Our earnings for rolling a 6 will be $10, and our earnings for rolling not a 6 will be negative $10, and or negative $1. And the reason that is because it says that you'll lose $1 if you don't roll a 6. So to use our formula, we just go E, our expected value, equals 10 a sub 1 times 1/6 plus negative 1 times 5/6, and that's going to equal 5/6, which, because we're talking about expected value, we're talking about the amount of money she's going to be earning, it's going to be about 0.83 cents. So what this is saying is every time Hannah plays this game, she should expect to earn 83 cents. And notice how that's not necessarily an option for what she's winning, but it's saying that over time, in the long run, each time she plays, she'll be earning 83 cents on average. All right, here's our second problem. It says a die is rolled and you receive $1 for each point that shows. What is your expectation? Let's do the same thing with E equals. So this little blank here will serve as if we rolled a 1, a 2, 3, a 4, a 5, or 6. So it's the same as all the die rolling problems. Our probability is going to be 1/6 for each one of these. And since we earn $1 for each point on the rolls, there's 1 point here, so you'll earn $1. You'll earn $2 here, and so forth. So now we just have to simplify, and the easy way to simplify this is to factor out the 1/6. 6 plus 5 plus 4 plus 3, which we've seen this before is 1/6, and this can be rewritten as 6 factorial, which is going to give us 21/6, which is $3.50. So playing this game, when you just play it once, you're expecting $3.50. Again, notice how it is not something that you actually can earn, but in the long run, that'll be what you do earn. All right, take a second, pause the screencast to read the problem, and then we'll get started. So it's asking us for our favorable condition is that we get to land on a multiple of 3. So on the spinner, there's 1, 2, 3 options to get a multiple of 3. So our probability of getting a multiple of 3 will be 3 out of the 8 total slots. The probability of getting not a multiple of 3 will be 5/8. Our payout for getting a multiple of 3, this is a new thing that you guys need to pay attention to. So you're going to win $3 if you land a multiple of 3. But the thing is, the difference here is that you've already paid in $1. So your net earnings are going to be $2. So I'll say that again. Since you started out with $1 to begin with, and you paid that in, even though you're getting $3 back, your net is going to be $2. So that's why our A sub 1 is going to be $2. And for the second one, not winning a multiple of 3, it says that you don't win anything, right? So you're going to be losing that $1 that you paid in, so it's going to be -$1. Now we can just use the same formula again. So we have E equals A sub 1, which is this $2 here, times the probability of landing on a multiple of 3, plus -1 for our A sub 2, our amount that we're earning for not landing on a multiple of 3, times the probability. When simplified, we get 11/8, which is about 1.375. Because we're talking about the expected value of our earnings and money, it would be $1.38. All right, this is our fourth problem. I'll give you a second to read this. You might want to pause it while you're doing this. So it says that when we play this game, we get $1. We get $36 if it lands on the number that you chose. So the probability of the number chosen is going to be 1, because you're only choosing one number, out of 37. The reason it's 37 is because there's 37 different spots that the ball could land on our wheel. Okay? And the probability of getting a not chosen number is going to be our complement to that. Or we could just know that there's 37 spots, so that's 36 out of 37. Our payout for getting the probability of the number chosen is, it says that we get $36, but again, we paid in $1 to play, so our net earning is going to be $35, and the payout for getting not chosen, we're not getting anything back, right? You win nothing, but because you paid in, it's going to be -$1. We set up our equation. E equals 35, our earning, times the probability, plus our earning for not chosen, times the probability, which equals -1/37, which means nothing to us because we're looking for expected value of winning the game in money, which is about -0.03 or -3 cents. So what this is saying is that over time, you are expected for each time you play to lose 3 cents. So this is very typical of a lot of casino games where you end up averaging less than what you'd be putting in. All right, finally, a safe containing $1 million is locked with a combination lock. You pay $1 for one guess at the 6-digit combination. That's going to be important. If you open the lock, you can keep the $1 million. And if it should say if you don't get the right lock, you're just losing that $1 you pay in. So what is your expectation? So to find the probability of getting that 6-digit lock correct, we're going to use the slot method. Okay, so it's 6 digits, and it's 0 through 9 are digits. So we have 10, and because you can the combination could be all 3s, for instance. There's 10 options for each slot, which is 10 to the 6th. So our probability for getting the right combination is 1 out of 10 to the 6th, which is 1 in 1 million. And that's just a coincidence that it's the same as the price. Okay, so our probability of getting the wrong combination, like the last problem, where we've only had a positive outcome and a negative outcome, it's the complement. So it'd be 1 minus our complement, which is 1 over 10 to the 6th, which is 999,999 out of 1 million. And so for this one, our payout, it's not going to be $1 million, right? You are going to be getting that much back, but remember that you paid in that $1. So our payout for if we get the right combination is this, and obviously this is before taxes. And then the payout for the wrong combination, you're not getting anything back, but remember that you did pay that $1, so it's going to be negative $1. So our expected value is 999 coming from here times the probability plus our expected value for getting a wrong combination times the probability equals, interestingly, 0. Okay, so your expectation is 0, so that means that there's a wash. This will rarely happen, but it is possible that your expectation could be $0. Good luck on your work.